production side, many people don't like something new. We made the pilot machine, and now this pilot machine made Rhenium. We need to understand how much Rhenium was extracted from the uranium. I cannot sleep when something is wrong. Science moves the world.
Kazakhstan is the world's leading producer of uranium. The country holds the top position by volume, accounting for more than 40% of global output. Kazakh uranium is supplied to dozens of countries and plays a vital role in the international nuclear energy sector. The in-situ leaching method allows uranium to be extracted without disturbing the landscape or using open-pit mines. A special solution with chemical reagents is injected into underground ore layers, where it dissolves the uranium. This uranium-rich solution is then brought to the surface for further processing. Along with uranium, other valuable elements are also brought up from underground. Until recently, they were returned back into the earth. The idea to change this approach became the foundation of a scientific project led by Kazakhstani scientist Armanbek Omirgali. He proposed using uranium-bearing solutions as a source of rhenium, a rare metal in high demand across the aerospace, oil and gas, and electronics industries. Until now, rhenium had never been extracted in Kazakhstan.
First of all, each technology of extraction is very difficult to use in different places. So this make the project unique because we can just take the same technology from other countries, because our liquids are not the same. And the chemicals, the process won't work similar anywhere. It will be different, and you need to change this technology. You need to check different methodics, different regime. We pour the liquid to mixing machine named extractors. We have many mixing machines, and they connected step by step. Using additional chemicals, we make the rhenium get some kind of powder. We made the pilot machine, and now this pilot machine made some rhenium. We make an analysis of these samples to understand how efficient this mixing machine and absorption columns was.
Rhenium is found in uranium solutions in the form of ions. To extract it, the process starts with ion exchange resin, which traps the rhenium ions. Then sulfuric acid is used to wash the rhenium off the resin, returning it into a cleaner solution. This liquid moves through a series of extractors where chemicals are added at each stage. They bind to the rhenium and help separate it from the rest of the mixture. Step by step, the solution becomes more refined. In the end, rhenium is precipitated and turns into a fine powder.
Before the starting of analysis, preparing the probe for analysis, I should check the humidity in the room. So I use this special equipment and I see the humidity, and I write it to special journal for the checking of the results should be compared to the humidity of the room. So it could be some corrections of digits depending the humidity of the room where it was made. I will show how we make analysis from rhenium that we extract from our uranium liquid. This is a device equipment to prepare the first step of preparing the probe for analysis for a count of rhenium in the rigid liquid. So we start from preparing the probe. We take this, this is probes. So At first step, we will take these probes. Then we will put this and add the probes till it will be 0.2 grams. That will be the next probe, next one. So we'll take the next probe. It should be 0.2. It will be enough. Okay. We'll take the next go. At this moment, we will make 4 probes, prepare 4 probes for analysis. We need to understand how much rhenium was extracted from the uranium, what the clearings, if there's additional elements in this extracted rhenium. The next step, I put the probe to the autoclave. I have 4 probes and I have 4 autoclaves. It is very important to have minimum 3 or 4 probes for analysis to make it, to have the real digits for comparison. Now I will make this ore liquid. It is important and necessary to do for make the analysis to rhenium in ICP. So I use at the first stage, I use hydrofluoric acid. I add the hydrofluoric acid to autoclave. We need to add the acid for 4 autoclaves, step by step. The last acid is perchloric acid, the same to 4 autoclaves. This we use these acids because of the type of our ore. It's the ore could be made liquid only with using of these 4 acids. And at the end, we'll use this to close autoclaves. It is very important to use a special autoclaves. It is a special material autoclaves that could work with the acids like hydrofluoric, sulfuric and other acids. My probes is ready for next step. The next step is using microwave. So we will now go to another room and continue the analyzing. Now I'll use the system of microwave digestation. So this system could analyze 12 probes, but we have 4 probes, so I use the scheme for 4 probes and put all probes to this system. Now we're connecting autoclaves to the system of microwave digestation. We put all autoclaves next to each other. The 3 connection points should be closed with special, and then we close. Now we will start the process. Now this machine will make the probe liquid. It will dissolution the ore with using of acids that I was add before. the machine using the heating with microwave and the circling system. So the probe will be dissolution equally. The process will take 1 hour and 40 minutes. The temperature is 180 degrees Celsius.
The final stage is sample analysis using an optical emission spectrometer. This equipment determines the exact concentration of rhenium in the liquid samples. The prepared solutions are placed into the system, and each test takes about 5 minutes. The results are displayed on the computer screen.
This is a window that show the spectra of standard rhenium sample. We see the yellow blank line, and we see the 3 blue lines. This is each line. It shows the spectrum that get by ICP system from each probes, and it build this line. It is a spectrum of rhenium.
Проект интересен тем, что впервые планируется.
This project is particularly interesting because for the first time it aims to recover rhenium as a byproduct from uranium solutions. It is a meaningful and promising initiative as it could open up a new line of business in the future. The experience gained from this project will also help explore opportunities for extracting other valuable byproduct elements. The methods being developed for rhenium can later be adapted and applied to projects involving other metals.
Использованы и применены в других проектах по другим металлам.
Armanbek Omirgali's school years were full of energy and curiosity. He won science competitions and enjoyed singing and drawing. After finishing school, he passed the entrance exams for an architecture program, but soon realized he was more drawn to exact sciences and technology and decided to change direction. Today, at 36, Armanbek confidently says that choosing science, and specifically mining, was the right and deliberate step in his life.
Greatest challenge was to finish my PhD dissertation, actually, and to get a PhD degree. It's a dissertation in field of production of uranium liquids. It's in about the process of desorption of uranium and cleaning of to get more efficiency in this field. It was a challenge for me because, first of all, it was new and it was interesting, and usually on production side, many people don't like something new. So when you come there to try to introduce something, to try to make experimental works, they don't like it because they say everything works good, everything works well, and we don't need it. So, but as a PhD student, I need to do it. The second part is that you need to make the work and you need to make the dissertation parallel, and the both of them need many time.
Today, Armanbek Omirgali works at a uranium production company in the Department of Science and Rare Metals. He often stays late at work, fully absorbed in his projects. But on weekends, he makes a point to disconnect, heading out into nature or meeting up with friends from a car club. Exploring new routes by car is something he truly enjoys. Just like in science, he's drawn to finding his own way where no ready-made solutions exist.
That there is two directions of science. Yes, it's a fundamental sciences and some kind of experimental science. So I'm more experimental science. I like physical experiments to see something new, to try something new. At this moment, at my job, I had possibility to realize many projects. I give ideas, I search ideas from different places, and it's very interesting for me every time, because to discover something new, it moves the history, it moves the world, everything. Science moves the world, actually. My main focus in My projects, it's of course industry. Technical projects, engineering science, there mostly is about production. So of course it should give more efficiency for production. But also I don't forget about the people, because every equipment that is developing, that was developed, should be safe, should be easy to use, and should be comfortable. I like to start new project. I like this feeling when I finish the project, when I see that the project is going well and is going as it was planned. It's hard to me to feel this feeling when the project goes not so good. It's very hard for me. I think more I cannot sleep when something is wrong, and I'm thinking how to correct it, to try to do something better. I believe and I hope that the science in Kazakhstan will get more interest and more support. It is very important to make understand our business that the science is very important and you should spend more. Maybe the project from 10 could be really effective, and it will cover all the expenses that you spend for 10 projects and give more for spend for another 10 projects.
To build stronger ties with industry, Dr. Omirgali makes time to present his projects. Recently, he spoke at a sectoral conference in Almaty, where he shared ideas for new scientific developments. The audience showed strong interest, and possible collaboration is now under discussion. In addition to domestic cooperation, international partnerships are also a key focus. Dr. Omirgali's team works with a French uranium company, and together they are carrying out more than 20 scientific projects.
I am really interested to collaborate with American and European institutions in field of, for example, projects in critical minerals direction, or some kind of development of equipment for extraction technologies and drilling technologies. It would be a really big opportunity to try to collaborate, for example, with Colorado Mining School. They have really big competence and big school of mine in USA. And with French and British colleagues in metallurgy, mining, geology. It's very interesting for me. I hope we'll have such opportunity. Science don't have nation. In science, first of all, we should be the friends, we should do the job, we should achieve our goals, we should find out new ideas together with many countries, work together, collaborate together, because every of us has something special, special knowledge, special experience that don't have a second one, and together we can do the real project and to make a new openings in science.
Armanbek Omirgali is a face of Kazakhstani science. He is developing a technology that makes it possible to extract not only uranium but also rhenium, a rare and highly valuable metal, from uranium-bearing solutions. Uranium is critical for aerospace, energy, and electronics industries. For uranium producers, this offers a way to generate additional revenue without building new infrastructure. In the long term, the same approach could be used to recover other rare metals, making natural resource extraction more complete, efficient, and forward-looking.